Hello. Before we get back into the Navier-Stokes equations, we need more preliminary background. And in this short lecture, it's on notation. That is the Einstein or index notation for partial differential equations. So why do we do this? The major advantage is that we'll be able to write equations and operations in a shorthand that generalizes dimensions and maybe saves a bit of headache and pain in our hands when we do a lot of writing of mathematics. And you'll see this is a little bit strange. It's different than vector notation if you haven't seen it before, but it's used heavily in the industry and research communities. So this is really important because it's the way we communicate. So the easiest way to look at it is just to generalize some vector notation and operations of vectors. And there's lots of this and lots of material online, but I'll just show what's most important. So first, let's just say that we have axis labels that might be x, y, and z in the x, y, and z directions of a grid. And we might say, well, x is x1, y is x2, and z is x3. So x1, x2, x3, that's very common. Instead of putting a 1, 2, or 3, we might just write x sub I and say, well, I varies 1 to 3. I mean, I could vary from, say, 1 to 1 or 1 to 10 if you had 1 or 10 dimensions respectively, but we'll mostly focus on 3 dimensions for the Navier-Stokes equations. Now, we know that there could be unit vectors, and some people might write n for unit vector, or e. Remember, that's just a single magnitude of 1 in a particular direction. If they're the unit basis vectors of the Cartesian coordinate system, we might write them e sub I hat. The sub I refers to the direction 1, 2, or 3 in the x, y, or z direction, x1, x2, x3, and the hat will denote that it's a magnitude of 1. So this is kind of the basic calculus 3 vector type thinking. So then these unit or basis vectors, as we might call them, we'll write as e sub 1 hat, e sub 2 hat, or e sub 3 hat. So sub means subscript, hat is the hat symbol that's above the character. Now, if we take the dot product of e hat 1, e hat 1, or e hat 2, e hat 2, or e hat 3, e hat 3, of course we'll get 1. That's not any different than multiplying two vectors in the same direction. They're the same magnitude. And 1 times 1 equals 1, of course. That's why we're saying 1. The dot product e hat 1, 2, 1, 3, 2, 3, or 3, 1, etc. will all result in 0, right? So that's like saying we have e hat 1 in the x direction and e hat 2 in the y direction, and their dot product by definition is 0. So that's a basic result from what's typically taught in the United States in Calculus 3. So this can be written in a short way. So we've kind of combined index notation with the traditional, like, I would call like vector notation. It's kind of awkward. You might say, is there easier ways to write this? Because we really haven't done much yet. Well, let's look at this particular figure just to remind ourselves. We have the directions x1, x2, x3, and this is just like a little box or domain perhaps, and it's decomposed for this vector a. So a is that vector a hat. Anyway, then we see, okay, well, a component of this vector a is a1 in the direction e1, a2 in the direction e2, x2, and the component of vector a is a sub 3 in direction x3 with normal unit vector e hat 3 basis vector. I'll take a second and look at that chart. Now, we want to be able to write these things more compactly, and this is where the idea of the Kronecker delta function comes out, and that'll be written as delta ij. So we're going to say, what is the properties of delta sub ij? That's right here. And if I equals j, delta ij, the Kronecker delta function for I equals j will be 1. So if I equals 1, j equals 1, I equals 1, say j equals something else. If I is j is 1, then it's 1. if ij is not equal to each other, say I is 1 and j is 3, then it'll be 0. So you can imagine there's about 9 combinations in 3 dimensions from the Kronecker delta function, and that would result in either 1 or 0. It only has really 2 arguments, I equals 1, or j equals 3, etc. Kronecker delta function. So why did we define it this way? Well, this allows us to write the dot product, inner product of our basis vectors or unit vectors, ei, and say ej as a Kronecker delta function. So if we take ei, say 1, and then replace the I over j to indicate another vector, if you will, and say j, we'll call it delta ij. So there's the operation. And that's for I equals j 1 to 3 for 3 dimensions. So you could make the maximum value of I or j to be the number of dimensions in your system. That's absolutely no problem. Kronecker delta function. Okay, so that's nice. So now we want to express our vectors, say like A in this graph, as the components of the vector times their basis vector summation. So here's the vector A, and A is equal to the vector component of A in the x direction, or one direction, times that unit basis vector, plus A2 times the unit basis vector in direction 2, plus 3, etc. And you can have higher dimensions if you wish. And we would write that as a summation. So this symbol here is summa, and we would go from I equals 1 to 3. And now you can see we've taken this operation and put it here. So we're going from 1 to 3, that's 1, 2, 3 of AI, times E1, E2, E3, which we write as E hat I, E hat I. So AI, E hat I, times the summation. Now you'll notice something interesting. This summation symbol is a very traditional way of writing things, right? So we're just summing the index I, or subscript I, from 1 to 3, put it in here, and we can expand and get the original vector. And this is kind of the way people usually learn. This is like a mixed notation, and we say, oh, well, we want to write this more compactly. So we don't have to write this summation symbol all the time. It's really annoying. So what do we do to maybe be a little bit more elegant? Well, we're going to create a new rule, and here it is. I'll box it. It's very important that repeated indices are always contained within summations. Or phrased differently, a repeated index implies summation. So the index here is I, and by repeated I mean there's a term, it's a one term, and I appears twice. Therefore, it's a repeated indice or index, and therefore I'll sum it and expand it. So I'll write this vector A hat, like up here, this way. I already said it's equal to the summation, but here's the new rule. We can write A hat as A-I-E-I hat. You'll see in here there's 2 summations of I. And we would sum it and write A1 E hat 1 plus A2 E hat 2 plus A3 E hat 3. So this is known as Einstein's convention, or this repeated index summation. Because I disappears really after the operation, it's called a dummy index. And that's because if it's repeated, it drops out of the equation, just like I showed previously. We could really call I anything we want. For example, we originally had A goes as AI, E hat, I, but we could also just replace the I with a J or I with a K. And since they're repeated, when I expand them out, I'll always get the same expanded form of the vector. Now that we have this notation, we can maybe think about how to write the scalar dot product in a longhand form and maybe express it more compactly. So let's look at the original vector notation. The vector A dotted with B. We would take A and B and write them in the notation we just defined. and we get the sum from I equals 1 to 3 of AI E hat I, dotted with the sum of j equals 1 to 3 of bj E hat j. How can we simplify this? Well, the summations might be written this way. It's a cumulative property, and we're really going to be multiplying them out. More compactly, we could take that EI hat, EJ hat, and write it as a Kronecker delta function as we just defined previously. Remember, for Kronecker delta function delta ij, if I equals j, it's 1, and it's otherwise 0. So let's just perform this summation here and expand it out. And we'll see what we get. We have the vector A dot B, and it's a cumulative property, right? Summation. It's the sum of a sum. And so we'll have 9 terms because there's 3 terms in each summation. So 3 times 3 is 9. And we get A1, B1, delta 1, 1, A1, B2, delta 1, 2, A1, B3, delta 1, 3, etc. You'll see that the trace, if we write it, it's not really like this, but just as an analogy, a trace would give us delta 3, 3, delta 2, 2, delta 1, 1. These are all 1. The Kronecker delta functions, say delta 1, 2, 1, 3, 3, 2, 3, 1, 2, 1, etc., are all 0. And so we're left with just A1, B1, delta 1, 1, plus A2, B2, delta 2, 2, it's a typo, and A3, delta 3, 3. So these values are 1. And let me just make sure I write that. So now we showed that A1, B1 plus A2, B2 plus A3, B3, as we've written this out, is really just, again, the summation of I equals 1 to 3. We don't have to choose I. We can do J or K or L or M or whatever of AI, BI, right? This is the same. But we can drop the summation because there's a repeated index and get AI, BI equals AJ, BJ plus AK, BK. So that's the dot product. Very compact. Let's look at more notation. We can always write it just like this as I showed. Now what if I want to do some other operations? I need to kind of see what happens with our Kronecker delta function before we do other things like cross products. Let's just say we set AI equals j everywhere in the expression, and writing more compactly and reducing things, we can do this product delta functions, or excuse me, Kronecker delta functions. So let's write delta ij, delta jk, delta ki. So we have I, j, k. So this one goes from I to j, j to k, and k to I. It loops back around. And you'll notice the order is very important. I becomes j before j before k, and k before I, because our system is I, j, k. And you think when I get to k, I'm going to loop right around. So this is like the forward permutation. You'll note later if I say things like kj, it's really the backward one. Okay? So that's something to remember for a second. So we'll say that delta ij, delta jk, delta ki goes as delta ik, delta ki. And that's because we can remove delta ij because we're setting I equals j everywhere. Then this would reduce because we have 2 repeated index as delta ii. That's we're removing delta ik because we can set k everywhere. So this type of thing would be delta ij, jk, ki goes as the sum of I equal 1 to 3, and that'll just give us 1 plus 1 plus 1 equals 3. Let's look at another example. Say we have a vector r and r hat in index notation. How do we express that? So let's express our new vector r in index notation. We'll say r goes as x1 e hat 1, x2 e hat 2, and x3 e hat 3. So these are the vector components of r. And we're going to just use x here. We could also use, say, r sub 1. That's fine too. And that's just, of course, the vector components written this way, the sum of them, right? The sum of the vector components is the vector. let's try and express that a little bit different in index notation. Let's try and write the unit vector of the vector r. Well, we know by definition that's the vector r, which has 3 components in this case, divided by its magnitude. So we'll take the vector r and leave it on the numerator, and the magnitude of that vector is its dot product to half. Well, we've already written our hat as x dot ei hat. We'll put that there, so that's still a vector. And its magnitude will be the dot product, which we derived earlier as xj, xj. And I'm going to use a different dummy index than I did up here for I. So the half power remains. So remember that dot product is nothing but the 2 vector components with a dummy index. Now this is really important. We did not use the same dummy index twice in the term. And you can think to yourself, what would I get if I used all i's instead of I here in the numerator and j in the denominator? Good question. Okay, so this is one way to write it compactly. That's the unit vector of r. Now what if we want to take, say, that a vector, we're going to take a new vector a and dot it with our unit vector. Well, we have this definition already, so we're going to put it here, and we can bring it down. And then now in the numerator we have a dot product, so you know this whole thing's going to be a scalar. Remember, this is a vector quantity, this is a scalar quantity, and that makes sense in our result. So we'll take this magnitude of the vector and put it down here, so that's the same definition, xj, xj half, and now our dot product of a dot r hat remains the same, that's ai xi. Notice again, we didn't use the same I index in the numerator and denominator. If we expand this out, what would it be? The numerator would be a1x1 plus a2x2 plus a3x3. The denominator would be x11 plus x22 plus x33, and I'll just put squares, all to the 1/2 power. Let's next look at cross products. So return to our definition of our basis or unit vectors in the 1, 2, 3, or x, y, and z low directions. So if you take the cross product of the 2 unit vectors in 1, 2, or 3 directions, by definition they'll be 0. If we do the cross products in the 1, 2, 2, 3, or 3, 1 directions, they'll just give, of course, the 3rd direction. So cross product of E1 hat with E2 hat will be E3 hat. And you can see this is like a permutation as I described earlier. If we go the other direction, say E2 with 1 cross product, we'll get the negative value, E3 hat. So there's some beautiful symmetry in these definitions. It's easy to remember it this way, I think. Now we're going to introduce something a bit new, and we're going to call it the permutation or cyclic tensor, or the Levi-Civati tensor. And that's going to be epsilon of I, j, k. Don't confuse epsilon with a small value. This is a tensor, epsilon I, j, k. And we're going to say, well, epsilon I, j, k is 1 if I, j, k is a cyclic or even permutation. Let's look at an example. If the permutation or cyclic is cyclic, then epsilon I, j, k will always be 1. And here are the examples and rules of what cyclic means. Epsilon 1, 2, 3, epsilon 2, 3, 1, epsilon 3, 1, 2 will all be unity. So look at the I, j, k values. I1, j2, k3, I2, j3, k1, and I3, j1, k2. You can see that from left to right, we're always going in increasing order of I, j, k. For example, I can just remember by looking at, say, it goes 2 to 1, or 2 to 1, or 3 to 2, decreasing values. That is, we're going from, say, 1 to 3, we're skipping something. That will get a negative 1. So that's the anti-cyclic behavior. So think of I, j, k, 1, 2, 3, or something like this. If we get 1, 3, 2, that's anticyclic, and this one's cyclic. You can see the pattern. If we have any repeated indices, it'll always be 0. For example, if we have 1, 1, 2, or 1, 1, 3, etc., there's no cyclic or anticyclic nature. The permutation tensor, or the Levitti-Civetta tensor is 0. Now let's try and take the cross products and definitions. So now, if we go back to E1 hat cross product E2 hat, up here, we know it's going to be E3, but we have to think about how to write this a bit more compactly. So it'll be an index notation, eliminate the vector notation. And that's done with this tensor. So E hat 1, E hat 2 will be this cross product. So we'll write the first index as 1 from here, the second index, the permutation tensor 2 from the 2, and then of course the third particular direction, which will be 3. And we know the cross product results in that vector 3. So this is really giving us a sign. It'll be 1, -1, or 0. That's the only possible values of the permutation tensor. Let's try another one. We have 1 and 3. I'll put 1, 3, and the remaining index is 2 multiplied by E hat 2. So you can see the pattern is very simple. So when you see cross products written this way, you'll know exactly what they mean. It means it's the cross product of the basis vector in the 2 direction with the 1 direction, which results in 3 and E hat 3. So this is a very compact way of writing the cross products in Einstein notation, which will be used. Okay, now this is interesting. We can write it as a general rule. We can write, hey, E hat I cross E j hat is I j k E hat k. Once again, we take the I and j and put them in the first part of the permutation tensor, and the third unused index we'll put as the remaining term in the permutation tensor, and with the corresponding unit vector or basis vector ek hat. So you can try if you want. This is going to be true for basically all the different types of expressions using permutations. So let's try another one just as a thought experiment. So remember, the permutation tensor, if it has 2 repeated indices, it's 0. So we take the cross product of, say, ei hat with ei hat. We write the first 2 permutations with I, and then we have a k values. So in here we would be summing from 1 to 3 of I and k separately. But remember, epsilon or permutation tensor I, j, j, k, k, if you will, are all 0. So you know by definition this is always 0, and therefore it's 0. And that makes sense because, of course, the cross product of 2 vectors which are similar should be 0. Using this, we can write it on a little bit different formula. Now, if we switch any 2 particular subscripts, it also reverses the sign of the particular permutation symbol, right? So we would say in words that permutation tensor ijk is antisymmetric, for example, in these situations, as I described previously. So epsilon ijk would be kij and jki. So let's consider our vector notation for cross products. We're going to now have 2 vectors and want to take the cross product of them. The first vector is A and the second is B. We previously defined these vectors in index notation. So vector A will be A sub I, E hat I, which, as you know, is A1 E hat 1 plus A2 E hat 2 plus A3 E hat 3. The same can be written for B. So here's our Einstein notation. So let's do the cross product. We take A cross B, and we'll take these and substitute them in here. And then we can substitute our definitions. We have AI, BJ, E hat I cross ej. So we see how we do this. Now, that will reduce to ai bj permutation epsilon ijk e hat k. So we can write our cross products in this general definition. And it's a good exercise to try and expand this out to see if you can make the leap too. And you'll have to do that, of course, with a 3x3 determinant matrix. So let's look at this. Remember, the kth component of A cross B would be A cross BK. So we could write that as epsilon ijk ai bj, where now I and j are only dummy indices. And you know that because I and j are repeated twice in the same expression. So we can write A cross B as a 3x3 matrix, and you see I missed A1, A2, A3 in here, and I apologize. And you could expand that out and write the cross product, which is, of course, the vector. We can also write this way, a new identity for two permutations. And that's very much like the cross product definition. Epsilon ijk, epsilon lmn is basically determinant of delta il, delta im, delta in, delta jl, delta jm, delta jn, delta kl, delta km, and delta kn. So this gives us all possible combinations of the indices and a resulting size of being equal. So let's look at this tensor and say what happens when n equals k. So we kind of introduce a dummy index. So that's k and n, ijk, lmn. So this is like the third index of both tensors. You can fill that in if you want and see what happens. And it means, of course, that we have a repeated index, and we'll have to repeat over k. Well, we write out our definition. Now we have kk, and we expand that out. How do we do that? We take the first times these two and these two. Then we take the second element minus the determinant of these elements, plus this element times these two. Now, if we write that out down here, as I described, and you cross out delta ij's as 0 when two indexes are not equal, and you'll have this. Epsilon ijk, epsilon lmk goes as delta il, delta jm minus delta im, delta jl. This is going to be important to remember in the future, but the summary of the most important operations that we've seen are right here. The dot product of two unit or basis vectors will go as delta ij. The cross product of two basis or unit vectors, I and j, will go as the permutation tensor times e hat k, the third index, which is not here, which we described. The corresponding dot product of two vectors, A and B, dot product will just be AI BI, which, as you know, results in a scalar because that's A1B1 plus A2B2 plus A3B3. The corresponding dot product, cross product of A cross B will be the permutation tensor times A, the components, AI BJ, times the unused vector k. So you see in here we have ijk, ai, bj, we put k. For example, if that was bk, we would put ej. So this is a very compact way. So now from when you see the Kronecker delta function, you think dot product of the unit vectors. When you see a permutation tensor times a normal vector, you'll think cross product of the basis or normal vectors of the Cartesian system. When you say AI, BI, or vectors like this, AI, BI, because remember AI and BI are vectors, you'll think the dot product. And finally, when you see a term like this, permutation tensor with two vectors in a particular direction, this just means, of course, the cross product of the two vectors in the orthogonal plane. Let's just look at some quick examples that you can work out for yourself. What if we have A dot B cross C is it equal to C dot A cross B, which is equal to B dot C cross A? Well, what we want to do is take each of these vector forms and put it in the permutation notation individually. So here's the one for A dot B cross C. And you can do the same operations just by changing the indices. It's very easy now. And the variable names for the vectors, A, B, C, interchange them, and you'll see you'll have, of course, equivalent results.